In the previous lecture, we learned about the switch mode converter. In the schematic of our switch mode converter, we use a symbol to represent the switch device. You might be curious about, in the practical circuits, how we realize the switch. Indeed, we use the power semiconductor devices to implement the switching function. So this is a very valuable question. So in today's lecture, we are going to learn about how to implement the switch devices using the mainstream power semiconductor devices. So first, we'll begin from the diode. So we'll talk about the power diode. Which is slightly different from the conventional PN junction diode. Indeed, we use the PIN diode. So first, let me plot a 2D view of the PIN diode. Suppose this is a semiconductor material, and the left-hand side is doped by the acceptors. So which will induce holes, positive type holes as the majority carriers. These acceptors are typically the group 5 elements. Group 3 elements. They can accept one electron to formulate a hole. So suppose the doping concentration for the acceptor elements is Na. Then the majority carrier concentration here, which is hole, will be equal to the Na, doping concentration. And on the right-hand side, we dope this part of semiconductor using donors. Doped by donors. So the donors will donate one electron to form electrons with negative charge as the majority carriers on the N side. So we use N to denote this type of semiconductor. So the donors are usually group 5 elements. And also suppose the doping concentration for the donors are Nd. Then the electron concentration will approximately equals to the Nd. So when the p-type silicon and n-type silicon are put together, the holes will diffuse to the N side and recombine with the electrons to form a space charge region. So we call this as depletion region. And similarly, the N side majority carriers, which are electrons, will also diffuse to the p side to recombine with the holes on the p side to form a space charge region. So together we call this region as depletion region. The depletion region means that the free charges are totally eliminated. Only ionized atoms are left. So they contain fixed charge, but there's no free carriers, so its carriers are depleted. So that's why we call this depletion region. And the depletion region will form a electrical field, right? From the N site to the P site to establish a built-in potential in this PN junction. And the built-in potential will cause the drift current, right? So in the neutral case, the drift current will counteract with the diffusion current. So eventually, the PN junction can reach an equilibrium. That's the basic principle of the PN junction. And for the power delt, we use the PIN junction. So the I means that based on the PN junction, we have an I layer, right, which is like a lightly doped N region. So we call this as N minus region. So that's why I plot the depletion region width on the N side much wider than the depletion region width on the P side, mainly because the dopant concentration here is light. Okay. So for the later on, I will tell you why we need such an I layer. Okay. So first, let's go back to the regular PN junction. We know that there is an exponential relationship between the PN junction current and the voltage. So there is an equation to describe. So junction current equals to saturation current times exponential lambda, the voltage bias, minus 1. And accordingly, we can plot the IV curve for the PN junction. So the x-axis is the voltage across the PN junction. Y-axis is the current. So as this equation indicates, there will be an exponential relationship. With the increase of forward bias, current will rise exponentially. And on the negative side, if V is negative number, this exponential I term is much smaller than 1, so this will be equals to minus IO. That is the basic IV curve for the PN delt. For PIN delt, it's about the same. There is one point I like to emphasize, which is the depletion region, right? So when the diode is reverse biased, meaning the diode is operating in this region, so the negative voltage is mainly dropped on the depletion region. So the reverse voltage is mainly blocked by the depletion region. So for the I layer here, meaning lightly doped. Lightly doped means that we can have a wide depletion region. So this means that we can achieve a high breakdown voltage. Which is a must for the power applications. In power applications, we need to bear high voltage in off mode. Okay. So next, let's look at what happens if the PIN diode is reverse biased. So reverse biased PIN diode, meaning that I would like to replot. So here is the junction P, N minus. So reverse biased means that we apply an external voltage source across this PN junction with the potential on the N side higher than the P side. That means reverse biased. So reverse biased PIN junction will incur higher voltage drop on the depletion region, right? So the depletion region will be extended. So originally it's here, now it's extended further. Extended. So originally it's this width. And the reverse biased incur the extension of the depletion region. So depletion region further expanded. So it means that this reverse voltage is dropped on this extended depletion region. So the reverse voltage appears across the expanded depletion region. And indeed, it's mainly dropped on the N minus region. On the N minus region. So that is the major functionality for this existence of the I layer or the N minus region, to enable higher breakdown voltage to allow the device to have a higher voltage rating. Okay. And besides the reverse biased condition, there is one thing I would like to emphasize, which is the parasitic capacitance of the PN junction. So we see that in the depletion region, we have ionized atoms here, right, which are positive, and here is negative, right? So those are denoted as Q. Q means charge, right? So the concentration here equals to the doping concentration, like ND. But now if we apply a reverse bias on top of the p-n junction, we will incur the extension of the depletion region, meaning that the Q, the charge will also be increased. So this feature is indeed a capacitor behavior, right? So because we know that the capacitor behavior means that the charge will change with the change of the voltage. You see here, if we change the external voltage bias, Q will change. So this will induce a junction capacitance behavior. Which is important and affect the switching performance of this device. Okay. So next, let's look at what happens if the p-n junction is forward biased. Forward biased means that we apply a positive potential on the P side. So here is P, here is N, here is N minus. Positive bias means that the external source have positive sign on the P side. A negative sign on the N side, that is forward biased. So in the forward biased condition, the depletion region will be squeezed, of course, right? So the depletion region will be narrower. P side, N side. So which allows the diffusion of holes across this depletion region to the inside, and also allows electrons to diffuse across the depletion region to the P side. So basically, the holes on the P side will be injected into the N minus region. Suppose there are originally holes, right? So the holes will diffuse, will cross to this side and to be exist on the N minus region. So this injected holes on the N minus region will have a very important function. So the injected holes effectively reduce the apparent resistivity in the N minus region. So there will be a lots of excess minority carriers on the N minus region. So this helps to, so those are the free carriers, right? So those can suppress the resistivity in the N- region, so which can reduce the on-state resistance of the diode. So we call this phenomena as conductivity modulation effect. So the conductivity modulation effect help the PIN diode to achieve low on-state resistance so that the device can carry large current in the on-state. Okay, now let's erase this blackboard. All right, we have erased the whiteboard. Now let's look at the switching behaviors of the PIN junction diode. So first, let's look at the turn-on transient. Of the PIN diode. So let's plot the voltage and current profiles in the turn-on process. So in the time domain, so first let's plot the voltage, and then we plot the current. Of the power diode. So originally the device is in off state, right? So meaning that the diode should bear a reverse voltage initially. And in this stage, since the diode is off, so the current will be equals to 0. And suppose at this moment, which is T0, the diode begins to be turned on. Since the diode is a semi-active device, right? The turning on mainly is induced by the change of the voltage. So if the voltage across the diode drops, then the diode will be turned on, right? So if the device is fully on, the voltage across it will be very small, like 0.7 volt, right? So almost 0. And the current will be a DC current. So those are clear, right? Here it's clear, here it's clear. The interesting is the middle part, the process of the turn-on transient. So there will be a profile of the diode current like this. It rises from 0 gradually, and then reach steady state current. So you can see that before the device is fully turned on, there is a stage, right? The I exists. So this IT has its function, right? This IT supplies charge to first decrease the voltage drop across the depletion region. Across depletion. Secondly, we need to have this IT to support the on-state current. right? In the on state, there will be a continuous current flowing through this PIN diode. We need to provide IT to support this DC current. And thirdly, we also need to invest IT to reduce the on-state resistance. This is mainly implemented by injecting the excess minority carriers. Minority carriers. As I previously mentioned, we need to have the holes on the N- region to establish the conductivity modulation effect to suppress the on-state resistance. So that is the turn-on process. Next, let's look at what happens in the turn-off process. Indeed, the turn-off process are usually associated with an effect which is called the reverse recovery effect. Reverse recovery. We can also use a time domain plane to illustrate this reverse recovery phenomena. Same, here is the voltage. In time domain. And here is the current. Also in time domain. So here is T0. The turn-on process are marked as T0 to T1. So this is the turn-on. Turn-off we also mark accordingly. So suppose here, before here, this is T2. So before T2, the device is in on state. So on state means that the voltage drop is very small, like here, right? So it's almost zero, like 0.7 volt. Current will be like here, a DC current. Then in this moment, T2, the device begins to be turned off. So first, we look at after it's fully turned off, what happens. So we denote this as the instant when the device is fully turned off. Suppose this is T4. So after T4, the device is turned off. So the voltage is reverse biased like this, right? And the current will be equals to 0. And now let's look at what happens from T2 to T4, which corresponds to the turn-off process. Indeed, this process can be divided into two sub-intervals. So here is T3. From T2 to T3, the voltage across it remain very small, close to 0. But the current begins to drop. So in this, from T2 to T3, we kind of remove or eliminate the excess minority carriers on both sides, right? But the voltage bias remain equals to 0. We consider that the device is still in on state. And after this moment, we still have a negative current. But in this region, the voltage across it begins to increase negatively to a steady state value. Okay, so in this region, it's like the depleted region is expanded. So we need to have an active current to provide the charge to allow the expansion of the depletion region. So it's like in this region, we built the blocking capability by extending the depletion region. So voltage increased negatively to a steady state value. Okay, so the two regions have charges associated with them, but for different functions, right? So this is for eliminate the minority carriers. This is for build the blocking capability. Together, from T2 to T4, we call this time integral as the reverse recovery process, and the duration for this is marked as TRR, reverse recovery time for the PIN diode. So we can see that if the diode is turned off, the minority carriers which was used for the conductivity modulation must be swept to resume the original state. So this will incur reverse recovery loss. So that is the major operating principle for the p-ion diode. Now let's have the summary. So first, for p-ion diode is a minority carrier device. So this means that for the N region or for the P region, we mainly utilize the depletion of the minority carriers to conduct current. Right? And secondly, it is able to achieve high blocking voltage or high voltage rating, mainly due to the introduction of the I layer. Right? I layer allows for high voltage rating. And thirdly, for the diode, we have the reverse recovery charge in the turn-off process. So these are associated with this process, reverse recovery process. So the reverse recovery time, TRR, will determines the switching speed, right? which is actually the bottleneck to determine the switching speed of the switching device. And fifth, we have a on-state forward voltage drop across the power diode. Usually, this voltage drop is higher than 0.7 volt. It's determined by the built-in potential and the voltage drop across the diode resistance. So this will incur a conduction loss. For the power diodes. Okay, so in this subsection, we learned about the models of the power semiconductor devices and also its on-state and off-state. So this is the most fundamental power semiconductor device. Understanding the switching on and off of power semiconductor device, like power MOSFET, is the fundamental for us to learn the more complicated devices.